Today we are going to be talking about generating Pythagorean triplets, and Pythagorean triplets are basically just a set of three numbers that fit into the Pythagorean theorem, which is of course a square plus b square equals c square, which corresponds to the triangle in that, let's say this is a, this is b, so the hypotenuse would be c. And just to give you a famous example, 3 square plus 4 square is 5 square, so the set of numbers 3, 4, 5 is a Pythagorean triplets. What we're going to be doing today is basically that we're going to come up with an algorithm or a procedure, a formula, such that when we follow that, we can get any Pythagorean triplet, we can generate any Pythagorean triplet. And we do that by considering two numbers, let's say s and t, where s is the bigger one of them. Both of these numbers are odd integers and they don't have any factor in common. So let's say s can be 1, s can be 3, t can be 1, s can be 5, t can be 1, let's say maybe 5 and 3, 7 and 5, and so on. So here our a, which is this side over here, would be 3 s times t, which is 3. This b would be 9 minus 1 over 2, which is 4. C would be 9 plus 1 over 2, which is 5. In the second row, this would be 5, this would be 12, this would be 13. Here, this would be 15, 8, 17. This would be 35, 12, and 37. So these all are Pythagorean triplets that we came up ourselves, given that we had choice over what odd numbers we took. And one more thing to notice is that these are primitive Pythagorean triplets. These are primitive Pythagorean triplets. Let me write PT. Let me write PPT. When I say primitive Pythagorean triplets, I mean that they don't have any factor in common. So for example, if I pick any triplet, let's just say 3, 4, 5, right? If I multiply this by any whole number, let's say I'm exaggerate the values by a factor of 2, this would be 6, 8, 10. This itself would be a new Pythagorean triplet, and it is easy to see because they're pretty much similar triangles. So I can keep on going. If I multiply this by 3, this would be 9, 12, 15, and so on and so forth, which of course follows that there are an infinite number of Pythagorean triplet. But what we are going to be doing today is coming up with these original Pythagorean triplets rather than their rip-offs that are a multiple of the original one. So, and of course, since I've already told you the procedure that we'll be following, that is using odd integers. Since there are an infinite number of odd integers, it will also follow that there are an infinite number of primitive Pythagorean triplets. So let me start off this by using some parity to show you that in a primitive Pythagorean triplet, it is always the case that the hypotenuse is an odd number and one of the two sides is an even number, which of course means one of the other side is an odd number. So let me say here that first of all, in a square plus b square equals c square, let's pick a and c to be, let's pick a to be odd, c would have to be odd basically. A and c must be odd and b must be even, given that it is PPT, right? So let's try to go ahead and make sense of this. When we look at a and b, well, either both of them can be even, or either it can be that it is an even odd situation. Let me write it like this, even odd situation. Or it can be that it is an odd situation. And of course, since we are adding these together, even squared is even, odd squared is odd. In the first case, c would be even. In the first case, c would be odd. In the third case, c would be even. Now, right off the bat, this is something nonsensical. This cannot be the case, because when we are talking about primitive ones, they don't have anything in common, but if they're all even, they would have 2 in common, right? This is something I claim that this will always be the case, so I would have to show that it is never the case that both of them are odd. And the reason behind this basically is that when we add 2 squared odds, the result is an even number, but it is only a multiple of 2. But when you square an even number, it is a multiple of 4. So what I'm really saying here is that, let's say a is 2x plus 1, b is 2y plus 1, c would be 2z, where x, y, z are odd numbers, odd integers. So it would follow that 2x plus 1 whole square plus 2y plus 1 whole square should equal 2z whole square, which means that 4x squared plus 4y squared plus 4x plus 4y plus 2 must equal 4z squared. However, if I divide this by 2, 2x squared plus 2y squared plus 2x plus 2y plus 1 equals 2z squared. Here we have arrived at a contradiction because this is an even number. This portion is also even, but when you add 1 to it, this becomes odd. So an odd number can of course not be equal to an even number. And so this means that this can never be the case. So we have proven that in the primitive case, A and C, I've taken A, of course it can be B and C, but let's just take A. A and C must be odd and B must be even. Next up, what I'm going to do is I'm going to reframe the Pythagorean triplet into something that might be more helpful to me. So I know that a square plus b square equals c square, but this would mean that a square is c square minus b square, which is of course c minus b into c plus b. And you'll see in a while why this is useful to us. Just to relate this to an example, if 3 square plus 4 square is 5 square, then 3 square is 5 minus 4 into 5 plus 4, which you can check is true. Let's take something else. Let's take 5, 12, 13. 5 square, notice how I'm taking the smaller one or the odd one. I'm basically taking a, which is the odd one. So 5 square would be 12 minus 13, 12 plus 13, which you can of course check is true. Let's just take a non-boring case where there's not a difference of 1. 35, 12, 37, 35 square, 37 minus 25 into 37 plus 25, right? Was this it? No, it was 12. Okay, so it was 12. 12. This means 35 square is 25 multiplied with 49. If you were to go on and do a little bit of experiment, you would realize that it is always the case. Let me write it like this: 1 into 3 squared, 1 squared into 3 squared, 1 squared into 5 squared. This is 5 squared into 7 squared. It is always the case that you are always multiplying two perfect squares, right? Here this was 1 square into 3 square, here it was 1 square into 5 square, here it is 5 square into 7 square, which I'm basically saying that it is always the case that c minus b is itself a square and c plus b is itself a square, which of course when you multiply two squares you get another square. Let's try to prove that it is never the case that c minus b is not a perfect square and c plus b is not a perfect square. Now, the way that I'm going to do it is basically showing that they do not have anything in common. Because if they do not have anything in common, it cannot be the case that when you multiply them together, you get something that is a square. So what I'm really saying is that c minus b will have something like the first prime squared, second prime, let's say power 4 and something. There wouldn't be any prime which has an odd power such that when you combine it with another prime, it basically becomes 4 and then you square root it, so it becomes a whole number. Right, so basically my aim here is to show that c minus b and c plus b cannot have something in common, which would be a proof that c minus b is a whole square and c plus b is a whole square given this situation. So let's try to do another proof by contradiction. Let's say c minus b and c plus b have something in common. Let's say the number d. So d would divide c minus b and d would also divide c plus b, which of course follows that d divides c minus b plus c plus b and that d divides c minus b c plus b minus c minus b, right? So this means that d divides 2c and that d divides 2b. Now we started off with the fact that c and b themselves are something primitive. They don't have anything in common. So then d can either be, the only thing that d can be is either 1 or 2, because they both have 2 in common. So d can be 2 or it can be 1. 1 is basically a case in our favor, because if they have a common factor of 1 and only 1, then that of course means that they don't have anything in common, because of course every number has 1 in common. So I need to show you right now that 2 is D cannot be 2 actually. And that is actually very easy to see, because if D is 2, that would mean that C minus B is an even number. That would mean that C minus B is an even number, and that C plus B is an even number. But that cannot be true, because in the first thing that we saw that C is odd and that B is even. So even minus odd is of course odd, and even plus odd is of course odd. So they cannot really be even, and hence they do not have anything in common, and hence C minus B is a whole square and C plus B is a whole square. Let me write this result down as C minus B is equal to sum T squared, and C plus B is equal to sum S squared, where T and S can be any odd number. Now, of course, from here we can follow up that since A was C minus B into C plus B, sorry, A square was C minus B into C plus B, A square must be S square T square. Therefore, A must be S multiplied with 3, which is our first thing. We know that, it is easy to do some simultaneous stuff. If we add these two together, 2C will be equal to T square plus S square. Therefore, C square is T square plus S square divided by 2. By the same logic, 2B would be, well, let's take this as minus. 2B would be S square minus T square. Therefore, B is S square minus T square divided by 2, which is our third result. And we have reached at the end, we have shown that given that S and T are any odd integers that do not have any factor in common, in the Pythagorean triplet, A would be those two multiplied together, B would be the difference of their squares divided by 2, and C would be the sum of their squares divided by 2. Of course, if you plug these results back into the Pythagorean theorem, the equality would hold, which would be, a testament, an assurance that yes, you are on the right path. So yeah, that's pretty much it. That's how you take any two odd numbers which don't have anything in common, and you come up with any Pythagorean triplet of your choice. It's actually raining outside, so this is the end of the video. See you in the next. I'll go enjoy the rain. Oh, forgot the QED. Bye.